Welcome to today's Explainer. We're going to dive into something that is literally all around us, atmospheric carbon dioxide. But listen, we aren't just going to look at it as some simple static gas. Oh no, it's a highly dynamic, absolutely critical system. We're going to dig into the math, the chemistry, and the biological realities of this molecule to really understand how it operates within our Earth's super delicate framework. Let's get started. Here's our quick roadmap for today. First, the rising carbon curve. Second, nature's delicate carbon balance. Third, the anthropogenic disruption. And finally, we'll wrap up with the physical and biological consequences.
All right, part 1, the rising carbon curve.
410 parts per million. I really want you to let that number sink in for a second. 410 ppm. That is the current concentration of atmospheric carbon dioxide. And this isn't just some random statistic to memorize. It's literally the baseline for every physical and biological process happening on Earth right now. Now, to really grasp why 410 is such a big deal, we have to look backward. For a massive chunk of human history, way before the Industrial Revolution kicked off, atmospheric carbon dioxide was sitting at a remarkably stable 280 parts per million. So this leap up to 410, it's a massive, mathematically significant systemic shift. We've surged from a long-standing baseline of 280 straight up to 410.
And the thing is, this system is incredibly active. We are currently tracking an increase of 1.8 parts per million every single year. When you're analyzing any dynamic system, the rate of change is honestly just as crucial as the absolute value. So, what's driving this mechanical engine? Mainly two massive scale actions: the widespread combustion of fossil fuels and extensive deforestation.
Moving on to part 2, nature's delicate carbon balance.
Now, nature's actually constantly producing its own carbon dioxide. You probably already know about respiration and volcanic eruptions, but let's talk about putrefaction. It's essentially the natural decay of organic matter. Basically, when living things die, they decay and they release carbon back into the environment. It is a completely fundamental natural source of carbon dioxide emissions.
So, you might be wondering, if nature is always producing CO2, why did those pre-industrial levels stay so stable? Well, it's because nature operates as this beautifully balanced equation. On one side, you have those natural sources, and on the exact opposite side, massive carbon sinks. Global photosynthesis, vast forests, and our oceans basically act as these enormous sponges. The emissions are perfectly offset by the absorption. It's an amazing equilibrium.
And it goes beyond just trees and oceans. We also have absolutely critical chemical sinks. Carbon dioxide is essentially locked away when it interacts with calcium 2+ and magnesium 2+ ions in the environment. It bonds and gets safely incorporated, literally pulling the gas right out of the air and locking it into solid natural compounds. This chemical incorporation is, for sure, a foundational pillar of the Earth's natural ability to regulate its own atmosphere.
That brings us to part 3, the anthropogenic disruption.
So here's the big question. What happens when new variables enter a balanced equation? Think about it. If the Earth has this perfectly matched system of natural sources and natural sinks, what actually occurs, mathematically and physically, when you introduce entirely new, unoffset sources of input? Well, in literally any scientific or engineering discipline, when you overload a system's capacity to balance itself, you get disruption.
These anthropogenic or human-driven variables are totally tipping the global scales, and it goes way beyond the obvious combustion of fossil fuels. Heavy industry plays a massive, massive role here. Things like the cement industry and widespread metallurgical operations where we're extracting and refining metals, they just pour unoffset CO2 directly into the atmosphere. It acts like a heavy thumb resting right on the scale.
Let's look at part 4, physical and biological consequences.
The macrophysical effect follows this really powerful two-step mechanism. Step 1, excess carbon dioxide acts as a greenhouse gas. Step 2, it traps heat. It really is that straightforward. The more this gas accumulates beyond the Earth's natural sink capacity, the more thermal energy is permanently retained within our atmospheric blanket.
But we have to remember, these consequences aren't just planetary, they are deeply physiological. As local CO2 concentrations spike, organisms actually have to increase their respiratory activity just to survive. And at very high concentrations, this naturally occurring gas literally becomes lethally toxic, directly inducing coma and death.
Carbon dioxide is such a wild paradox.
I mean, it's the absolute foundation of life-sustaining photosynthesis, and yet when it gets overloaded by industrial variables, it transforms into a lethal disruption. Which kind of leaves us with a critical, undeniable question. If our natural, biological, and chemical sinks are already operating at maximum capacity, where exactly will the next 100 parts per million go? Thank you so much for joining me for this explainer.